Welcome all. We are in the course on computer-aided decision support systems. We are discussing about big data analytics and the decision support systems. How does the big data or humongous amount of data that is there in different fields is handled or is contracted to have a specific or useful output out of it. In this lecture and in this week, I will discuss the decision support system in computer-aided design and computer-aided manufacturing, the big data analytics, how does it helps in the contemporary computer-aided manufacturing systems. We will start from the geometric modeling, an introduction to what is geometric modeling and how it is a core in the product design process. Then big data analytics in the computer aided design. The computer aided design in general, we use AutoCAD starting from point, line, surface, volume or so. We now use new algorithms, new methods such as convolutional neural networks, artificial bee colony. Such heuristics could be used with the advent of the big data analytics that could be handled using the modern technology. Then data exchange formats in computer aided design and computer aided manufacturing. When computer aided design communicates with the manufacturing, that is the machine, that is the CNC machines, then comes the part programming. The part programming, how is that supported by the CAD, computer aided design, that we have made in that DSS for the part programming we will discuss in this week. Geometric modeling. Geometric is a mathematical term. When we say geometry, it is the collection of points, lines, circles or so. Modeling, when we try to collect them to get into a specific shape, that is geometric modeling. So, geometric modeling is a mathematical representation of an object's geometry. This is created by a computer or a piece of software, then we call it as geometric modeling, or we also call it computer aided design when specific geometric models are collected together to get some information that is useful. So, it helps us to collect the information that is both graphical and text based. We get graphical and text based information. This goes as input to geometric modeling. So, in the product design process, or when we have suppose some ideas are there, for instance, if you need to design a new mobile phone or need to design a new car or maybe need to design a new chair, the ideas for that would be there. That ideas has to go through design analysis. Design analysis means the curves that you are putting for your mobile phone, are those actually able to be manufactured or not? So, do they fall in specific mathematical models or not? If not mathematical model, that could be manufactured through maybe additive manufacturing. The CNC programs generally go to the 5-axis level of the machining. So, there also the complex shape could be shaped, but sometimes some of the shapes which are very organic or so could not be manufactured. So, the design that you are presenting, is it mathematically presentable or not? If it is there, that could be directly converted to a CNC program and we can have a codes, part programming codes out of that could be manufactured in a production. The core or the heart of all these three ideas, production and design analysis, here we have at the center is geometric modeling. So, geometric modeling tries to work for the entire manufacturing process. It depends heavily on the computer aided engineering. The purpose of computer engineering or CAE has changed so much over time that various applications have been now created based upon the usage and the execution. So, one of the most used CAE application is actually geometric modeling, the computer aided engineering. If I say, if I have designed anything, I have only come up with a shape that I think could be manufactured. But computer aided engineering is one that we put here in the design analysis, that helps us to have the understanding or analysis on the model that we have developed to see whether the model would be manufactured rightly or not, or if it is manufactured, what would be strength at various points. For instance, this is a model of pen only. In the pen, this is the fit. If I click it, there is a sound fit. This is known as push fit. It has to be a push fit. That means the tolerance, the dimension that is given to this projection and this serration that is given here, it has to be overlapping. That means interference has to be there. So, this kind of things, using a computer aided engineering itself, what is the force that is required to push the pen in, what is the size of the screws that we have put here is required, what should be the dimension on of the pen, what should be the length of the pen, how do we put the colors and everything, that could be seen in the computer aided engineering only. So, modeling helps to have the exact dimensions. This is a pen, maybe 12 mm of diameter, maybe 120 centimeters of the length, and the cap of the pen. How do we put it? How do we click it? How do we put it in the paper, in the pocket, the pen holder, everything? How do we design? When have the complete dimensions, that is the geometric modeling has helped us to bring this into the existence, bring this into the reality, and later computer aided design, the design analysis helps us to develop programs to manufacture them in the production. So, information is ingested in the graphical and in the text based formats both. So, this data is presented as picture and kept in a database. So, geometric model is a picture, or I would say image. There are certain product exchange data forms or the formats IGES, DXF. I will just talk about them in the coming lectures. So, those formats goes into the computer aided manufacturing system, that is my CNC machine, to manufacture the component. So, that is in the image form only. The object can then be altered and subjected to various analysis. Alterations using various analysis. I would say analysis as a plural, SES. Geometric modeling frequently employs curves to build surfaces because they are simple to manipulate and they can be bent to suit the application. A set of points or analytic functions or other functions can be all used to create curves. The object's mathematical representation can be seen on any computer, and then it can be used to generate drawings that can be then analyzed, and ultimately it can be manufactured in our production system. So, to create a geometric model, there are generally 3 typical steps. Number 1, we use commands such as points, lines, circles. These are the commands used to create the geometrical elements. Next is these points or the elements that we have created now have to be put into a specific shape. For instance, we have created cones or pyramid prisms, or we have created the shape of the pen that I have, the cap. Now, this has to be rotated and transformed to the various requirements. Then we use rotation scaling, upscale or downscale, and other transformations. Then we use a variety of commands to build a geometric model in which we integrate the model components to create a desired shape. Then we try to assemble or integrate. The word assembly is only used in computer-aided design if the components have different elements in it. For instance, this cap and the body, this put together is an assembly. This cap having its main body and its holder is not called as assembly because this is a single component. This I could just call as integration of a cylindrical or a cylindrical shape with a straight flat shape here. Integration with a small gap in between them. So this is integration. So these commands are used components to create desired shape. These can be helpful to generate the models which are in two specific kinds, that is 2D or two-dimensional or 3D, what we call as three-dimensional. 2D is used for flat objects and projects two-dimensional view. The file format generally is DXF, and 3D is a model in which intricate geometry can be also seen, and it is completely viewable in 3 dimensions using a image form itself. Solid modeling is primary method for 3D geometric modeling. So 3D computer program is used to describe geometric relationships and the physical scope of a component when building a geometric model in CAD, and there are various formats such as IGES, STEP, in SolidWorks, SLDPRT, solid part, so on. A component's properties such as its mass properties, other physical properties can often be calculated using the CAD software in which computer-aided engineering module is integrated. Geometric modeling types, I would say, are of majorly 3 kinds. Number 1, wireframe modeling. It is a straightforward modeling system that uses only lines to represent the object. So straightforward, it is also known as line model representation. So wireframe modeling is only used to describe wiring system because it cannot adequately express complex solids. So small businesses that need to design products with intricate surface details generally consider wireframe modeling as a part of it. Next is the surface modeling. This is a kind of a modeling which represents the object as it appears on its surface, as is implied to describe the object with clear understanding of its manufacturing. Surface modeling is used to produce the objects with intricate forms. For instance, the big objects such as the car bodies, ship bodies, or airplane bodies, the outer surface, how would that look like? That is represented using surface modeling. Inside of the body, what are those that will be presented by solid modeling. In surface modeling, we have the curves such as Bezier, which are mathematical curves, or B-splines. So the engineer organizes the edges so that it characterizes the polygonal surfaces in the surface modeling. In the solid modeling, which is also known as volume modeling, the complete model could be described. Multiple sides of an object can be built simultaneously using solid modeling tools. Surface modeling is less ambiguous when using solid models with them, which can create multiple sides at once. In solid modeling, there are certain topology rules that are used. For example, a cube has 6 faces, or the specific radius, the numerous radii of the cube. If this is the pen, the example that I am taking, so this is the radii of the pen, the radii of the back of the pen. This outer radii has to match with this inner radii, because it doesn't know much feel that the component is different. Then there is a step in it. What is this radii? This all comes in the outer surface only, in a way, right? So this could be put it in a surface modeling, but inside do we have threads, and what is the shape, what is the thickness of this? So this is a plastic component. It is manufactured through the molding process, so pen molding. So generally in the injection molding, these are manufactured, the plastic pens or so. So for those, what is the thickness that is required, the allowances for the thickness, those tolerances also comes into play in the solid modeling. So let me start with the wireframe modeling, a little introduction to that. In the wireframe modeling, the user enters 3D vertices and joins the vertices to create a 3D object that is known as wireframe. The wireframe models lack the surface definition because it is only the outer frame of the model. So how does it start? It starts to connect points, lines and curves. When I say points, point could be anything. If I need to define a point, let me say I have x, y and z axis, x, y, z. There is a point A here in the space which is of the coordinate x, y and z. Or I can have a point B and another point in space C. This B has coordinates x1, y1, z1. There is another point C which is this distance from B, whose coordinates could be x2, y2 and z2. Or I can say there is a point which is center of a shape. This is another point, I will name it D, x, y, z. Point could be maybe on the circumference of the circle as well. This is a circle, here do we have point, and the distance from the center, we can say this is a point, and from distance from circle there is an angle to it, I would say angle theta. Or it could be a point that is at an angle to the origin. So it could be at any space mathematically. If I try to present line or a line segment is the connection between 2 points. In general, this is a definition. So we have a point A and point B. When we try to connect them, A is x1, y1, z1, B is x2, y2, z2. Or it could be a line parallel to another line. There is a line, the distance between two lines, and this is a line that is parallel to it, starting from a point D, x, y, z. Or it could be a line that is tangent to a circle and starting from a point at a distance from the circle, let me say E, x, y, z. Maybe it could be tangent to two circles F, G, x1, y1, z1, then G is x2, y2, z2. Similarly, the curves could be there. Very simple curve. If I try to start with, circle is a very simple form of the curve which is concentric, which is having one common center, and the distance from the center is all equal, which is known as the radius of the circle. So this curve, let me start. It could be a circle with center A, x, y, z and radius r. or it could be a circle with center and a point at the diameter. I will call it point B, x1, y1, z1, or C, x2, y2, z2. Or a circle could be drawn through 3 points. This is general mathematics. If we have 3 points with a in center of these, that is the point at center here, so we can draw a circle with these 3 points. Give me a circle. Let me call the points D, E, F with dimensions x1, y1, z1, x2, y2, z2, and x3, y3, z3. Or a circle could be joined with a tangent with a center G, X, Y, Z. Or if two lines are there, we know the diameter of the circle. A circle could be put here with a specific radius. So anyways, we can represent the circles. These are two lines which are and having an in circle here. So these two circles might also have an in circle between them, of which radius is fixed. I am trying to represent this because these only coordinates A, B, or connecting the coordinates E, D, F to make a circle would lead us to have geometric shapes which we try to connect together, which we try to interlink together to have the final shape of the object. That brings us the wireframe model. Wireframe model can be converted to a surface model, then it could be maybe converted to a solid model to have a final program that is used as a support systems for the production. The decision support systems, where to alter, which circle is cut or so, is starting from here itself. This is a very fundamental. The 3D drawing model can be matched to its reference using the wireframe modeling. Once created a wireframe model, the planar objects in the single plane can be transferred to a 3D location. This enables the creator to see whether the reference through the model or match the vertex points to align with the desired shapes or desired references. So this helps us to have a quick and simple way to illustrate the concepts, how the model would look like, in place of having a long detailed solid model and then to precisely construct the model or so. So while skipping the detailed work in wireframe modeling, one can present a very basic framework that is easy to make and understandable by others. So we can make a solid or surface model that has specific shape using a wireframe model as our geometry. So we can, let me say, I will put a model here. So this is like, suppose if this is a model, this is a mobile phone, and this is a full solid model in which full mobile phone is there, body is there. If I just try to connect its vertices and try to have a wire, a surface wire here, then another wireframe here, another wireframe here, and it is only one wire, this it will look as a rectangle wire, right? Then here also it will look as a rectangle. From each side different views would be there. So we can have different views. For instance, let me draw a body of which different views can be seen. Let me say the different views that could be seen could be orthogonal, isometric. Let me say this is an isometric view of a model. Isometric means we have view from the top, view from the side and view from the front, all of them in one view. Isometric, all of them are equally distributed. We can have orthogonal view of them as well. This is isometric. Let me say orthogonal. Orthogonal would have its top view. From the top it would look like something this. From the front it would look like this.
I would say this is front view, this is top view, this is side view. Now this is my top view, this is front view, and from the side it would look like this. A hidden line inside. This is side view. This is orthogonal. And up we have the isometric. If we have just these lines only, that is a wireframe model. Or we can have maybe more frames here. We can have one more frame here, second frame, a third frame, a fourth frame. So this is my wireframe model. If this is completely filled, it is a solid model. If it is a complete surface only, then it is a surface model. Now, if I try to cut my solid model, for instance, this is my solid model, if I try to cut it, I would see in the wireframe model only the points of the wire. And if it is a surface model, I will see this surface only. In the solid model, I will see the complete solid. For instance, if I am cutting a brick with a papers or maybe a saw, let me say I have a brick model here. That plane is, let me say, a plane or a paper. And the other side of the brick would look like something this. So, this is a brick being cut with a plane of a paper. If I try to see only half cut view of it, how would that look like in the case of wireframe, surface and solid model? I would say wireframe, surface and solid. In the case of wireframe, let me make the other side of the brick behind the plane. This is the cutting plane and the other side of the brick in red color. So here what would I see? I would only see wires here. 2 points of the wire at the top on both left and right side. Then this wire here and the inner part of the brick. In case of surface model, it would show me the complete surface when I join these points. So if I join these, I will see this surface. In the case of the solid model, what would I have? A complete solid. Here the points are connected. The points are there just like the wireframe before, like if I connect them, these makes the wireframe to a surface. If I try to have a solid model, I will see a complete field solid here. So this is the solid modeling. Wireframe, surface and solid modeling. Next is in the surface modeling, the object appears to be a solid, but it is less sophisticated than the complete solid modeling. So despite being more complex, because of the fact that surface and solid models have same appearance, the surface cannot be cut into open just like solid models. So the curves which I mentioned before, B-splines or Bezier or nubs, which are also B-splines, these allow computer to translate commands into the mathematical models. I showed you the mathematical coordinates because the arcs are converted into the mathematical models, which are taken as codes which are known as G or M codes in the part programming. So these are taken by the computer and mathematical models are made out of them. These models are stored in files and always available for editing or analysis at any point when we require. The surface modeling enables precise adjustments to challenging surfaces. So typical procedure is we create the model by combining the solid as surfaces in 3 dimension. The model is converted into surfaces by utilizing associative modeling. And then we confirm the flaws and surface tools. So these are generally used to mold the castings, the complex objects like cars, ships, aeroplane bodies or so. So the basic castings in which surface of the casting is required, those are made by the surface modeling. Then users can view all the surface points at once with surface modeling. The models are imported from another CAD system as well, occasionally where the features are lacked. In these situations, the desired changes can be made on one or more model faces by applying surface modeling techniques. So building one face at a time using surface modeling allows for precise control over the contour and direction of any face. So multi-resolution modeling could also be developed through it. So not going into much detail, I will move to the solid modeling and we will see in the assembly support systems how does different models helps us to have a geometry that is useful in manufacturing. In the solid modeling, the nodes, edges, surfaces are combined to get the volume of the object that is being designed. So topology rules are necessary for solid modeling to ensure that all covers are properly sewn together. This method of modeling geometry is based upon the idea of half space. That is, starting with a solid model is pieced together using topology rules. This is a complex method known as topological design or so. So complex shapes geometry can be quickly calculated. For instance, a cube has 6 faces or not, or we can have a connection between various faces. So it is represented generally in 2 ways, solid modeling. One is constructive solid geometry. Next is boundary representation. When I say constructed solid geometry, the primary solid objects such as prism, cylinder, cone, sphere, etc. So they combine together to have a constructive or construction on each other to create a final solid shape. These shapes are either included or removed to have a constructive solid geometry. Next is the boundary representation. The boundary representation means the object's spatial boundaries serves its definition in building up the model. It gives an order to rotate, sweep. Generally the CAD models that you use this kind of method, the boundary representation, where you rotate, sweep, blind facets, you extrude, cut, extrude. Various facets into the three-dimensional solid which describes at various again points, edges or surfaces as a volume. These surfaces can be combined to create a surface that expressly encloses a volume, complete volume, which I showed you in the previous slide. The most popular form of the geometric modeling in 3 dimensions is solid modeling only, where the calculations for the various engineering inputs such as for the moment of inertia, for the mass of the object, for the weight of the object, for the density of the object, for the putting into the software what is the material, calculating a temperature it could conduct, temperature it could resist. So the conductivity, the insulation, not resistance, insulation to that specific temperature, that could also be put. These solid models helps us to do the computer aided engineering part like system dynamic analysis. So creation of codes, when I say codes, these codes could be the G codes or maybe for the robotics, etc. If robotics movements have to be given, those codes are generated. Then assembly simulation, These are all supported by solid modeling type. Solid modeling can confirm whether two objects occupy the same space by storing both topological and geometric information. It can also enhance the visualization. So enhances the design quality, and that has a potential to automate or integrate the different functions. So different kind of the techniques are there for the solid modeling, different kinds of softwares are available. I would like to take a break here and would discuss the assembly support systems, how are those developed and how does big data analytics with a small cases or studies or examples I will say helps in having a new era of the computer aided design. Let us talk about that in the next lecture. Thank you.